Hola todos. Welcome, everyone. Today, we're going to talk about memory, how it works, how to think about it, and how smart decisions can raise your performance by as much as 50 times. First, a couple of quick introductions. My name is Richard, and I'm a principal developer at Unity, where I've worked for the past 11 years or so. I've worked on many things at Unity, and I'm one of the people responsible for our overall technical strategy and architectural evolution. And I'll let my co-presenter Dan introduce himself.
Hi, I'm Dan Violet-Sagmuller. I was really hoping to be able to present here today alongside Richard Fine, but unfortunately I'm unable to make it, and he'll take over on the entirety of the presentation, except for a few video clips where I'll show up. Let's talk about a small tech demo that I was working on, Vigilante Racer. Maybe it'll become a real game that goes out there, maybe not, but it's something fun that I've enjoyed playing, and it's an anti-gravity racing game where the cars can drive around on walls and ceilings, and it does this by raycast to raycast different points out. Now, every single vehicle in the game was having to run between 100 to 1,000 raycasts to be able to distinguish and understand the shape of the world around it. I was getting capped off at about 200 cars, but I wanted to get that up to 10,000. That was a challenge I put for myself when I started getting into recreating a physics engine that was operating with low-level memory, data-oriented design, all things that go into the modern physics engine anyway. But in this case, it was designed specifically for the anti-gravity racing. I was able to go well over 10,000. That was a single-threaded game. This was all in C#. We were getting into low-level memory in order to make this number work. That has more to do with DoD, data-oriented design. DoD is about taking the user experience, the code that produces that user experience, and bringing it as close to the hardware level as you can. What areas of that memory are slow? What areas of the CPU are fast? And how to take advantage of that. The closer you can get it to there, the more it's going to be like the circuits of the computer were printed for that game. Most of the time, you're not going to be achieving numbers like this. You'll be looking at trying to achieve a few extra milliseconds in a frame. Quite a lot of times, you're using the physics for how that physics works. So this presentation is going to be all about that low-level hardware memory, how that part works and how you reach it and work with it in C#. And it's your job to figure out how your game and your ideas can get closer and closer to that from your new understandings.
Thank you, Dan. Here's a little bit of footage from Vigilante Racer. This is just one car, but as Dan said, the goal was to have 10,000 of these running in real time. We'll hear more later about how Dan leveraged a deep understanding of memory and CPU behavior to design his physics engine and achieve massive performance gains that let him not just hit, but surpass that goal. Before that, we'll cover some theory. First, we'll quickly recap how memory works on modern devices. Then we'll talk about object-oriented programming and object graphs and how they are laid out in memory. We'll talk through how garbage collection works, both in Unity and in modern.NET. And lastly, we'll use our new understanding of memory to talk through some techniques and guidelines that can help you improve performance significantly. So let's begin with a quick recap of memory. Now, this might be familiar to many of you, especially if you've spent any time in the past several years watching any of our talks about data-oriented design, things from Mike Acton and so on, but a refresher never hurts. I'll make it quick. Many people tend to think of memory as a sort of amorphous blob, a kind of single massive array of bytes. Now, that's true in a way, but there are some important properties of the hardware that everyone should know about. So let's break down what's going on inside the CPU. Firstly, we've got the arithmetic logic unit, the part of the CPU that actually carries out the individual instructions, adding, multiplying, dividing, etc. Then we've got registers. This is a small block of memory that holds the values the CPU is actually operating on right now. Different architectures have different sets of registers. An x64 PC has 16 general-purpose 64-bit registers, plus 16 128-bit registers for floating point operations, while something like Apple Silicon has 31 general-purpose 64-bit registers and 32 128-bit Neon registers for SIMD operations. Next, the cache, or more accurately, the caches, because there are multiple levels of cache. The lowest level, what we call L1, is typically exclusive to a CPU core, and it's the smallest, from 16 to 128 kilobytes. Higher levels, L2, L3, and so on, are larger, but shared between CPU cores. Now, the ALU typically cannot operate on values in the cache directly, but instead must load them into the registers, operate on them, and then store them back into the cache. Now, the cache is intended to always be a partial replica of main memory, a copy of specific data regions that the CPU needs to work with. So while the ALU is responsible for loading and storing the data in the cache, a separate unit called the Memory Management Unit, or MMU, is responsible for maintaining the cache by copying data over the bus from main memory into the cache when needed, and copying data from the cache back over the bus to main memory after it was modified. The MMU copies data across the bus in blocks, typically 64 or 128 bytes, called cache lines. If the ALU wants to access data which is already in the cache, we call that a cache hit. And if the data isn't in the cache and needs to be fetched by the MMU, we call that a cache miss. It's important to understand the different performance implications here. When the ALU accesses data in the registers, that's free, typically requiring no additional time above the execution of the instruction itself. Accessing the caches is a little more costly, but not much more. A few cycles for the additional load and store instructions. But if we have a cache miss and need the MMU to go and fetch data from main memory, that can be hundreds of cycles, depending on your device architecture. The CPU has a range of tricks to try and stay busy while it waits, but there is no way around having to wait for the data to be available before you can operate on it. You could think about it like this. The registers are like the CPU's hands that it can use to hold what it's working on right now. Caches are like the CPU's desk. And then main memory is like a massive archive in the basement of another building in a different city. A bus ride away, so to speak. If you structure your data the right way, you can reduce the amount of time you spend waiting for fetches from main memory. Now, there is another implication, which is that sometimes it can actually be faster to recompute something than to read it from memory. Now, this is usually a micro-optimization, so we're not going to focus on it today. We'll focus on the structure issue. Let's talk about how object-oriented code is typically structured in memory. Now, I said before that people think of memory like a single massive array, and that's true in a sense. From the program's point of view, it is like a big array of bytes, which it indexes using memory addresses. Now, a byte can only hold 256 values, so when we want to store data with a larger range than that, say an integer, we use multiple consecutive bytes, and the CPU breaks the value up across them transparently to us. An int needs 4 bytes, so it goes in maybe memory addresses 8 through 11. A long needs 8 bytes, so maybe it goes in memory addresses 24 through 31. And when we're dealing with a C# struct containing multiple variables, those variables are laid out sequentially in memory, one after the other. For example, vector 3 is made of 3 floats, each of which needs 4 bytes of storage, so it looks like this. Now, there are some situations where this isn't quite true, where the compiler will do things like leave gaps so that your variables are aligned to nice round memory addresses, but we won't go into that today. Now, what about a string? The problem with string is that the amount of storage that it needs is going to vary, depending on how long the string is. If we have a string in a struct, and we try storing its data sequentially with the other variables, like we did with vector, we either have to guess how much space we need, which means we risk not having enough space, or reserving space we don't need, wasting memory. And if we try dynamically allocating space once we know how big the string needs to be, we have to keep moving the score variable around. And any code which wants to access the score variable also needs to check the length of the string so it knows where to find the score variable in memory, and this is not very efficient. The solution is to store the data elsewhere in memory and record the address we stored it at. This is called a pointer, and it allows us to resize or move the storage for the string data itself without it affecting anything else in our struct. You don't use pointers in C# often, but you do use their friendlier, simpler cousin, references. References are pointers in disguise, hiding the details of memory addresses and preventing you from treating memory like a raw array of bytes. So the important implication here is that when you're dealing with structures of variables of primitive types like int and float, you can assume that they're going to live near each other in memory. And it means that they're likely to be in the same cache line. So once you've accessed one variable, accessing other variables in the same struct is probably going to be pretty fast, as the CPU will have loaded them into the cache already. But as soon as you have variables of reference types, strings, arrays, classes, accessing data through those variables may mean you're reaching somewhere totally different in memory, and you need to load new cache lines in order to read them, paying that 180 plus cycle cost. Let's look at an example. Here's a simple monobehavior component which contains variables A and B. We'll assume that those other variables are reference types, which means that A and B are references to objects somewhere else in memory. When the update method starts to run, the first thing we're asking the CPU to do is access this .A. This loads the cache line containing the variable A, which potentially means we're waiting 180 plus cycles. Then, now that A is loaded, we can access the object it is referencing to read the isTrue value from it. This object is somewhere else in memory, meaning that we may likely need to load a new cache line in order to read it, waiting another 180 plus cycles. Then we move on to accessing this .b. Both reference variables are going to be stored near each other in memory, if not sequentially. So the chances are pretty good that both variables are part of the same cache line. And so when we access this .a to pull it into the cache, we've probably also pulled in this .b at the same time. Even if we got unlucky and we're straddling two cache lines, the next cache line was likely prefetched. More on that shortly. So we can probably access this .b now without needing to load any additional cache lines. However, when we access the object that this .b is referencing in order to read its isTrue value, we again are accessing an object somewhere else in memory, likely pulling in yet another cache line and waiting another 180 plus cycles. So what looked like a very simple line of code, just testing a couple of Boolean variables, which alone only takes a handful of cycles, may have incurred 3 cache misses, taking more than 500 cycles to complete. We probably couldn't avoid having at least one cache miss in this situation, but if those Booleans were stored in our SomeComponent class instead of being on other objects, we could have perhaps been 3 times faster. Now, I mentioned something about prefetching on the previous slide. Let's talk about it more a little for a second. We've talked about the MMU fetching data from main memory into the cache whenever there is a cache miss. But this suggests that the rest of the time the MMU is just sitting around doing nothing, and that's not true. A lot of work goes into trying to predict what data you might need next and prefetching it so that when you go to access it, you don't get a cache miss. There are 2 main approaches to prefetching at the hardware level. Sequential prefetching is simple and just prefetches the cache lines after the one that you just loaded, typically keeping them in a separate cache called a stream buffer, where they can be pulled into the cache far more quickly than going all the way over the bus to main memory. Strided prefetching is more complex, and it involves looking at patterns in the memory addresses that you're accessing in order to predict what you're going to need next. Now, the implementations of prefetching are diverse across different CPUs, so it's tough to optimize for any individual prefetching strategy. But what you can generally rely on is that the more your data access patterns are simple and predictable, the better the CPU will be able to recognize what you're doing and prefetch for it. A pattern like read every value in this array from start to finish is something the CPU is probably going to detect, while random memory accesses following an object graph all over memory is going to be much trickier, much less predictable. One C# specific note about this: beware of how for each can sometimes hide random access patterns. If you're using for each to iterate over a linear collection like an array or a list where the data is all laid out in one block in memory, then that's fine. But if you're using it to iterate over a more complex collection, like, say, a linked list, then while it might seem conceptually like you're working through something linear, in practice your memory accesses are going all over the place. Now, complex collection isn't guaranteed to be bad. The implementation for dictionary, for example, is implemented as a linear list, but that's an implementation detail. It's not something dictionary guarantees for you. So if you're looking at something performance sensitive, it's best to explicitly choose collections that commit to a linear layout. Let's switch tracks for a bit and talk about another topic key to memory in Unity: garbage collection. One of the big problems in memory management is knowing when is it safe to reuse memory for a new purpose. There are 2 main approaches to this problem. The first is explicit. We, as programmers, decide when we're done with some chunk of memory, and we signal that it should now be freed, made available for reuse. Now, this is the usual model in languages like C, But you do see it appear as a pattern in Unity. When you explicitly destroy an object, for example, you're signaling to the engine that it can free the memory used by the object and use it for other purposes. C# itself also has the iDisposable pattern. It's often hidden behind syntactic sugar like using statements, but it is also a kind of explicit lifetime management. Now the other is implicit. The program doesn't say when we can free memory, but we figure it out somehow. One example of this is a reference counting approach, where we keep a track of how many systems are using a block of memory, and we free the memory when the count reaches 0. However, the approach that I think almost everyone in this room will be more familiar with in Unity is tracing garbage collection, which works on the principle that any memory which is unreachable by your program, which has no variables referencing it, can be freed. So how do we actually do that? Let's walk through the Berm garbage collector, which is the garbage collector used by both Mono and R2CPP. Here's a bunch of objects in memory that may need to be freed up. Berm uses what is called a two-phase mark and sweep approach. The goal of the mark approach is to find all of the objects that the program could access and mark them. The process starts from a number of known routes that the program can access. For example, static fields, variables on the stack. In Unity's case, this also includes all of the managed objects that Unity is keeping alive from native code. For example, the C# portion of your mono behavior components attached to objects in the scene. Then we visit the references stored in those objects. Now, the way that we use Berm is precise, which means that we tell it exactly where it should look in each object to find references, and it can completely skip objects that it knows don't contain any references. Then we repeat the process with those referenced objects, working transitively until we run out of references to visit. Once this marking phase is done, the collector can do the second phase, the sweep, iterating through all the allocated memory blocks and freeing any that did not get marked. Now, in reality, Berm doesn't do all of this work immediately. It frees larger allocations immediately, but some smaller allocations it defers until later for performance reasons. And also, freeing an allocation does not necessarily mean that we release the memory back to the OS. We may hold on to the page and use it for future allocations instead. So all of this works, but reading through the entire object graph in order to mark reachable objects is slow. And it also requires that we stop the world or pause execution of managed code until it's complete, because we don't want the object graph to change while we're in the middle of marking things, as this could create false negatives. This stopping the world is the infamous GC spike that you may be familiar with. Now, in Unity 2019, we introduced the incremental GC for all platforms except web. This is still using the Berm collector, but it splits the marking phase into two passes. Firstly, it does one marking pass while the managed code is still running, time slicing the work. Now, the results of this pass are, as we just said, not completely correct, because our changes to objects mean our marking might be incorrect. But we also keep a record of which objects we are modifying, or more accurately, which memory regions we're modifying, so that if our marking is incorrect, we know where it could be incorrect. Because we know where changes occurred, we can then go back and reprocess these modified objects to eliminate any false negatives. We only need to traverse the part of the graph that changed, not the whole graph. Now, it's possible a program could keep modifying references faster than we can rescan them. So after a while, we do still stop the world and finish processing any remaining modified objects. We also recheck objects referenced from volatile routes like CPU registers and stack memory. But this is typically quick, because as soon as we find we're referencing an object we've already processed, we don't need to look any further. So once we've processed all our remaining modified objects and rechecked our routes, we can be confident that we have a marking that didn't miss any used objects, and we can sweep just like before. Using the incremental GC means we pay a tiny additional cost when we change the value of a reference variable to record that we modified that memory region, but in exchange, we stop the world for much less time, meaning much smaller GC spikes. Let's also take a minute to talk about the core CLR GC, coming to a technical preview of the Unity player in 2026. Core CLR's GC also marks objects, similar to Berm, but it takes the idea of only traverse part of the graph one step further, introducing the concept of generations. The idea is that a program tends to have a bunch of long-lived objects, which are rarely ready to be collected. And so we can save a bit of time by just assuming that they're still needed, treating them as routes from which we only need to care about marking the shorter-lived objects. Core CLR classifies objects into 3 generations. Gen 0 is for newly created, short-lived objects, while Gen 2 is for our longest-lived objects. We run the garbage collection process on each generation at different frequencies. Because Gen 0 is where we'll find the most garbage, we run the GC there frequently, while at Gen 2, we'll rarely have garbage to collect, so we don't GC it as often. When we're collecting Gen 0, we assume that everything in Gen 1 and Gen 2 should already be kept, and just use their references as routes. So the mark phase completes quickly, because short-lived objects tend not to have many references, and because any references that they have to longer-lived objects don't need to be explored further. Once we've finished marking Gen 0, it's time to free up memory, and this is the other big difference with Core CLR. Instead of sweeping through the allocations and freeing unreachable objects, Core CLR is a moving and compacting GC, which means that instead, it copies marked objects to a new location in memory. Now, it packs them tightly together when it does this, which means the resulting objects take up as little memory as possible. And as a side effect, it also makes life much simpler when allocating new objects, because there is no need to find a free space. You just put it at the end always. It's then also able to quickly blow away all the old objects in a single operation, instead of needing to do any bookkeeping for individual free objects. The surviving objects are also at the same time promoted from Gen 0 to Gen 1. We assume that if they survived one GC, they might not be short-lived after all. If they survive a Gen 1 GC, they'll be promoted again to Gen 2. The potential downside is that because the objects moved in memory, the GC also has to make sure that all the references to them get updated. However, most of the time, if you have many references to an object, that object is probably also pretty long-lived, meaning it will be in Gen 2, meaning it doesn't get collected very often, and is likely not to need moving, because the objects it got packed together with are also all still alive. One last note on GC. When we talk about GC, we normally mean the GC that is used to clean up your C# objects, but there's actually a second GC in Unity. We call it the asset GC, and it's used for cleaning up Unity objects that are no longer needed. At runtime, this GC runs when you call resources.unload unused assets, as well as when loading a new scene non-additively. In the editor, we run whenever memory pressure gets too high, as well as at other times, such as when creating a new scene or when completing an asset bundle build. The asset GC is a simple mark and sweep system, like naive Berm, and doesn't support incremental or generational collections. It uses Unity's serialization system to understand when native objects are referencing each other, for example, like a material referencing a texture. It also piggybacks on top of Berm on the C# side, using Berm's existing marking functionality to discover when managed objects are referencing assets that should be kept alive. So let's start talking through some details about how you can leverage this stuff in your projects. Now, some of this requires unsafe mode. Unsafe allows you to do particular things that break the rules of the .NET runtime. If you do them correctly, you can improve performance and everything is fine. If you do them incorrectly, you can screw things up in a way that the runtime cannot help you with. So instead of getting nice exceptions when you do something wrong, you can cause hard crashes, buffer overruns, dangling pointers, security incidents, all of the fun stuff that many of us are using C# to avoid in the first place. So be careful. For our purposes, you can think of unsafe as giving us more memory control. You can't use it if it's not on, so you can turn it on globally for your project or on a per assembly definition basis. So let's look at something you can do with unsafe. Here's one of the data structures from Dan's vehicle physics engine for his game Vigilante Racer. Now, if you remember, we want 10,000 cars in this game. Each car has, amongst other things not shown here, multiple engines. So initially, we're storing them in an array. Now, what does the memory layout of this look like? It's an array, a reference type. So our car structure is there at the top, but the engine data is somewhere else in memory, and car is just storing a pointer to it. Each of the engines in the array stores the position of the engine relative to the car, but it also stores some thrusters. Now again, this is an array, so again, the actual array data is stored somewhere else in memory, and the engine just points at that data. So the end result is that the data for our single car instance is scattered across 6 different places in memory, which means that when the vehicle physics engine is processing that car, it's very possibly hitting 6 cache misses as it goes to access each part of the data for that one car. This happens because of the arrays. We're using structs, so everything is tightly packed, but the arrays being reference types breaks that up. Can we do better than that? Let's look at what Dan settled on. C# allows you to declare what is called a fixed size buffer in a struct. What that does is allow you to directly pack an array of a primitive type, in this case an array of bytes, sequentially into your struct instead of the runtime allocating it somewhere else and storing a pointer to it. You have to specify the size explicitly. As we saw with string, if the size can't be predicted, it causes all manner of problems. Dan worked out the size of his structures by adding the sizes of the individual fields. Now, while C# does have a size of operator, you can't use it at compile time. Then he declared byte arrays big enough to hold the necessary number of instances of each type, 7 thrusters and 4 engines. The result is that all the memory allocated for a car is now in a single large block, instead of being scattered across different locations. Now, of course, there's obviously a big problem with this. Car is no longer actually using the engine type anymore. So if we have a car instance, how do we get at the individual fields of an engine or a thruster? The solution Dan came up with was to add a function that reinterprets the bytes as a more useful type. There's 2 key tricks in use here. Firstly, the function uses the new ref returns feature introduced in C#7. Now, ordinarily, if a function returns a value type, like thruster, a struct, that return value is a copy of whatever we returned. By using a ref return, we return a reference to the original data itself, allowing the calling code to read and write the structure instance itself instead of modifying the copy. Secondly, we use a little bit of pointer magic to conjure up a reference to a thruster. Let's go through that in a bit more detail. The fixed keyword is used to get a pointer to the beginning of the thruster data buffer. And that buffer is maybe here in memory. We use a fixed statement block to tell the runtime that it's not allowed to move that data right now because we're taking a pointer to it. Now, this is not an issue for the Berm GC, which doesn't move things around in memory. But for a moving compacting GC like Core CLR, it's a big deal. So the C# language spec requires that we pin a buffer if we're taking a pointer to it to give itself the freedom to use a moving compacting GC in some situations. Note that because we're getting a raw pointer and can do all kinds of unsafe things with it, we can only use this fixed statement in an unsafe context. We had to enable it for the assembly. We had to mark the function as unsafe. So the pointer we get is a pointer to the raw bytes of the thruster data, the address in memory of the beginning of the buffer. Next, we're casting that pointer from pointer to bytes to pointer to thruster. So instead of pointing to something that is 1 byte long, we're pointing to something that is 28 bytes long. It doesn't change the actual value of the pointer, but it will change the way that the compiler interprets it, as we'll see in a moment. Having converted the pointer from a pointer to bytes into a pointer to thruster, we can then index it, just like an array. Because we've told C# that we're dealing with thrusters instead of bytes, it automatically calculates the offset within the buffer based on the size of a thruster. So we go from a pointer to the beginning of the buffer to a pointer to the specific thruster we asked for. And lastly, as we're returning the value, we convert from a pointer to a ref, effectively locking down the pointer so that calling code is no longer allowed to do things like unsafe casts with it. This is how we get the result back out to a safe context. So as long as our byte buffer was big enough, and as long as we don't try to access an index which is out of range, we'll end up returning a reference to a section of our byte buffer reinterpreted as a thruster, which we can use without needing to turn off the safeties in our calling code.
So I want to emphasize that the specifics of exactly how this physics engine work aren't really what matters here. What matters is the specific nature of how you get your game down to the hardware level as close as possible. What that's going to look like for your game will be different from mine. However, as just a quick overview, this operates really similar to sign distance function, which basically just says how far you are from a particular object. Now, that's a function, typically not done as a memory system, where it's jumping through triangles. But in our case, I'm using something I call PRF, proximity repulsion field, which is almost identical, except it returns the fully formed physics. It's normal, the direction it's supposed to be heading, and the amount of power to apply in that direction. Ground is easy. If the y coordinate ever drops low enough to whatever your ground height position is, then you're going to return a normal of up and a power based on however close it is to the ground. Rather than jumping around triangles in memory, trying to find out which triangles collide, I just break the world into chunks, and each one of those chunks holds a small array of what functions it can use, plus the minimal amount of data it needs for those functions to operate. We can figure out exactly where to go in the array based on the position. Just a simple hash function can determine the exact index without having to look up any memory. If you still want to dive in further to that, I'll have references at the end of the presentation for it.
Let's look at a couple of other techniques that might be useful. The first one was actually also part of Dan's strategy, but it was subtle, so you might have missed it. The use of struct instead of class. We looked at this code snippet and how the use of arrays could end up with data spread across 6 different blocks in memory. But there's an even worse universe that we could have started in, where these things were classes instead of structs. As classes, these would all be reference types, which means that an array of engines or thrusters would no longer be arrays of those things tightly packed together. They would be arrays of references. So our car would hold a reference to an array, which would be a set of references to engines, which would themselves each hold a reference to an array, which would be references to the actual thruster object. Good luck prefetching that one. And of course, because these would all be references, there'd also be a lot more work for the GC to do. Using structs instead of classes can reduce this kind of referencing mess and help to minimize how much work the GC has to do in its mark phase. But it's a double-edged sword. You can't store a direct reference to a struct. However, what you can do is store the index of that struct within its buffer, and if you need it, a reference to the buffer that holds it. Managing those indexes can still be a little difficult, but at least you have more control and can pick an allocation scheme that fits well with your use case. And speaking of having buffers where you access things by index, I do, of course, need to mention Unity's entities package, which is a whole programming framework built around the idea of have big buffers of structs and index into them. In ECS, you have entities, which are really just indexes, used to access your components, which are structs packed into big buffers. And then, when you're working with these things, you're encouraged to write your code as systems, which loop over your components in a way that is specifically designed to be friendly to the prefetcher. Now, there's already tons of resources out there about Unity ECS, so I won't go into more detail now. I'll just note that it's entirely possible to adopt ECS for just a part of your game. You don't need to use it for everything. And there are also other third-party ECS solutions out there for Unity other than the official entities package, if you prefer. Now, suppose you take the advice about structs to heart and start reorganizing a lot of your code base around using structs. And potentially you start to end up with some pretty big structs containing lots of different things for different situations. You might have a struct representing a character, and in there you've got their position, their health, their stats, their emotional state, the number of pancakes they had for breakfast, etc. And then suppose you want to loop over all your characters to do something, like update their positions. So you're accessing maybe the first 12 bytes of a 200-byte structure. Now, this is not terrible for the MMU. Strided prefetching means it can recognize that you're accessing addresses at 200-byte intervals, and it can prefetch the pages that you need. However, it's a bit wasteful from a cache line point of view. If a cache line is 64 bytes, then when you go to read those first 12 bytes, the MMU is loading 52 bytes that you never actually needed. And every entry in the list is a new cache line. So instead, consider splitting the struct up so that instead of one big buffer containing instances of your massive struct, you have a set of buffers that each contains some part of the data. One buffer for the positions, one for all the stats, one for all the pancakes, etc. Now, when you start looping through all the 12-byte position entries, your 64-byte cache line means you're loading in 5 and a bit entries at a time, which is both faster and also means evicting fewer other things from the cache in the process. We often hear this pattern described as being the difference between an array of structs, what we had initially, versus a structure of arrays, where we split the data of our individual entries up into different arrays. It's also sometimes helpful to think about hot versus cold data, data that you use often, like positions, versus data that you use rarely, like pancake breakfasts. Splitting the two up can mean that when you load your hot data into the CPU cache, you avoid wasting any cache line capacity loading cold data that is probably not useful to cache. Cold pancakes. We're nearly done. Here's a few closing thoughts. There is a tension between performance and flexibility. We've talked about how getting the best performance means structuring your data in a way that fits the way you'll use it. But if you keep changing your mind about what the data is or how you're going to use it, you'll need to change your code too. So you have to be smart about when to lock down a system and commit to a design that you can optimize heavily, and when to keep things a bit lighter because the game design might yet change. It can be fun to see how far you can push performance with these techniques, but it's also important not to lose sight of the larger context. Don't fall into the trap of trying to optimize something that is only 1% of your average frame time when you could be looking at the thing that takes up 15%. The lower level you go, the more susceptible you are to the details of different hardware. What might give you a boost on x64 might be slower or even unstable on mobile devices. Test on the platforms you're actually targeting and use all the tools at your disposal to measure what's going on. Not just the Unity profiler, but other tools like Apple Instruments or Superluminal and so on. It's not easy to find out things like this line of C# code is causing lots of cache misses, unfortunately. You have to do some detective work, cobble together information from multiple sources, like looking at how your Alta CPP generated code is being processed to try and deduce what's going on. Pursue big architectural wins as your top priority, not micro-optimizations. Architecture and data design changes are more impactful and also less painful to maintain. Collaborate with your designers and artists. Keep them informed about your performance constraints and the assumptions that you're building around. Content optimization is a thing, and you cannot break the laws of physics, no matter how fun the result might be. I'll let Dan have the last word, and then we'll move to Q&A.
I used to think performance was easy, that it just kind of clicked and made sense. And to a large degree, I was correct if the position of the objects actually lined up properly in memory. But I don't get to dictate that. And it would be very difficult for any system underneath this all to intelligently figure out where to organize my memory for me. But once I started realizing what the structure of memory was that I'm trying to get everything to match up with, it started making me question everything. Even string reverse came into question. So if you have larger strings that for whatever reason you want to reverse, does it make sense then to grab a chunk of memory from the beginning, pull 64 bytes of that data, and pull 64 bytes of the data from the end of the array, and reverse those, and then grab 64 byte chunks, moving all the way until you get to something that takes less than 128 bytes? Would that be faster? Honestly, I don't know. I haven't tried it. If it became important to whatever system I was running, then I would run a test to go evaluate that. Honestly, this ended up becoming a lot of fun during certain architectural challenges where we're taking a process and we're considering how performant is this going to be. This is an area where we need to manipulate a lot of memory really effectively. And so we start questioning and assigning weights to how the memory is processing at certain times. How many CPU cycles we suspect this will take. In some cases, we don't really know. In most cases, we don't really know. That's part of the reason that we need to evaluate this. But we can make educated guesses. But don't forget that these are guesses. You have to check the data or it's effectively useless. If your system's going out to a game console, then you've got a really locked definition of what that is going to be. If you're going out to mobile, to WebGL, to Windows, to Mac, to Linux, you're just pushing out to every possible thing that it can potentially run on, I'm not sure it's that reasonable to do this. It's also really important to realize that not all games need this. It is important to have this in mind during your initial designs of the architecture. Where are the key areas of how you're organizing your memory and jumping around from spot to spot? Are there some areas that you can consider very early on in how you architect and design that? Because some of those will be hard to get around later on. And finally, if you're interested in going into a deeper dive from how I went to 200 to 10,000, I do have an article up on my blog that goes into a lot of detail to exactly how that works, how the memory was structured, source code examples. And you can also find information about this on my YouTube channel. Keep in mind that the specific details of exactly how I implemented that aren't what matters. It is your design and how you get that down to the hardware level as close as you can. Hopefully today we've opened some doors to help you find your own way there.
And that's it. Thank you very much, everybody.